My name is Reece Elling, and I work both with Seth Stein and Chris Scotese. So I'll highlight just a little bit of work that I've done with both of them. The earlier parts of the summer and then the stuff I'm doing now with Chris. But we submitted a paper back in June looking at Central North America's three major failed and buried rifts. The Mid-Continent Rift here, which has kind of been the topic of my study the past few years, and then the Southern Oklahoma Locogen and Reelfoot Rift. And we get questions asking about how these rifts compare at many conferences. So we've been looking at what properties of continental rift evolution can be generalized from these, focusing primarily on their gravity anomalies. So if we look at their average gravity signatures, which is plotted here on the bottom graph, we have the west arm of the Mid-Continent Rift in purple, Southern Oklahoma Locogen in green, east arm of the MCR in black, and we see those exhibit these pretty high positive anomalies, whereas the Reelfoot Rift here doesn't really exhibit any. So we've been looking at creating some average gravity models for each of these rift structures and looking at how they compare. And what we found is that overall they look grossly similar with very similar tectonic origins and structural features. We have major central rift basins, a lot of volcanic igneous rocks filling these basins, this underplated gray feature, but they do have some interesting differences that highlight different aspects of their evolution, such as differing igneous rock volumes. You'll see the west arm of the MCR here in the top left has way more igneous material than, say, the Reelfoot Rift, which has very few. And they also have different amounts of extension. Another example would be the Southern Oklahoma Locogen is believed to have been inverted about 12 kilometers post-failure, whereas the Reelfoot Rift, that little volcanic material sits buried beneath the surface and was never inverted and brought to the surface. So that's part of the reason why we expect it to not have a gravity anomaly. And then looking at the project I've been working on with Chris, we've focused more on the paleomagnetic data and the global plate motion modeling that we did a few years ago, and now using it to test the longstanding question of whether cusps in apparent polar wander paths reflect tectonic events such as major rifts or collisions. So this is Laurentia, or present day that's called North America, basically. This is the apparent polar wander path of that. And a common cusp that people look at is this one at about 1100 million years ago called the Logan Loop. And that's often linked to the Grenville orogeny and the Mid-Continent Rift. And if we plot major tectonic events that have occurred throughout the history of North America, visually these appear to line up pretty well with these cusps. So a lot of people have indicated that that's likely a good link. Where we have a cusp, there was likely a tectonic event. But we've been really trying to analyze this deeper to prove that relationship and looking at how the velocity of the path changes throughout history. This is 0 to 1500 million years on the right. This middle graph here, how the azimuth or direction of the cusp is changing. Then most importantly, looking at the delta azimuth or the actual changes in direction of the apparent polar wander path and looking at how the instantaneous changes might correlate to the collisions or rifts that have occurred throughout that plate's history. And the way we're testing this is by comparing the observed geologic events here in this middle graph. These red dashed lines are all of the observed major tectonic events throughout Laurentia's history. With then these black lines are the major directional changes greater than 60 degrees. So when the apparent polar wander path or the path of the plate changes directions greater than 60 degrees, that becomes a black bar here in this middle graph. And these are the observed tectonic events. You see that those oftentimes appear either right on some of these cusps or very near to. So that's really promising. And at 60-degree cutoff, that's this middle column here, 60-degree cusp angle cutoff. There's an average delta T, or that time shift between the event and cusp, of only 13 million years. That's a really good link. Whereas if you'll see this bottom graph, if we randomly run a test of the same number of events, but randomly place them anywhere throughout its history, we see overall a lot higher a lot higher delta T's, or a lot higher average time shifts of those randomized tests than the observed ones. So that's a pretty significant relationship that we're seeing, at least with Laurentia. And we're at time, so I'll take any questions.